Introduce you to the interim director, unless we have new news, and you can correct me anytime here. Interim director for Green Bank Observatory, and Dr. Tony Remijan. Previously served as NSF's assistant director for science support and research. Okay. As a prominent astronomer and scientist, was in Charlottesville, Virginia. Earned his undergraduate and PhD at the University of Illinois. Taught and held positions at NASA. So we got some NASA colleagues here in the house, by the way, Tony. He did join NRAO as a postdoctorate researcher, became a staff scientist and held leadership positions such as division head for scientific user support and research and deputy assistant director for the North American ATMA Large Millimeter Submillimeter Array Science Center. And he did play a crucial role in commissioning the ATMA Large Millimeter Submillimeter Array ALMA. He has made significant contributions to the field of astrochemistry, particularly in the study of complex molecules in space. His research has implications for understanding the chemical precursors to life, stellar nurseries, and planet-forming regions. As a leader at NRAO, Dr. Remijan is involved in expanding science-ready data products, implementation, overseeing the telescope time allocation process, and developing science environment to support research needs. His scientific research and expertise extends to NRAO and the Green Bank Observatory instruments, including the Green Bank Telescope and science programs. So, Sarah, please welcome Dr. Remijan. We appreciate it.
Thanks, Andrews. Well, it's kind of impressive to hear that played out like that. Thank you very much. So I'm really happy to be here. This is your last talk and last day. Yikes. Okay, and you're still in it. You're still here. We're good. We're awake, maybe. So I don't want to monologue too much, Nicole. We can make it more of a discussion type topic. So if you want to talk about astrochemistry, the first things that come to your mind when you hear astrochemistry is what? Anything, especially recently in the news.
Large molecules.
Amino acids, large molecules. We've been following JWST lately. Atmosphere of exoplanets. What did they find in the atmosphere of exoplanets? Hydrocarbons. What else? Sulfur compounds, particularly dimethyl sulfide and deuterated dimethyl sulfide in the atmosphere of these exoplanets. Detected with JWST. Phosphorus. Where do they find phosphorus? Maybe not JWST, but where was phosphorus found? Specifically, where was phosphine found in our solar system?
Venus.
Type Venus. So if you find phosphine on Venus, in the atmosphere of Venus, it absolutely has to be what? Yes. What did they say? If you found phosphine on Venus, it absolutely had to be what? Life. Ouch. Yeah. You find dimethyl sulfide in the atmosphere of an exoplanet, and I have a lot of issues with the detection of that dimethyl sulfide, but that's a whole other discussion. It has to be what? Life. I'm going to try to emphasize for you that, with the whole history of astrochemistry, just because you find a molecule in space, possibly organic molecule in space, even if you find an amino acid, which you have never done in like the interstellar medium in space, it doesn't necessarily mean that there is life. Thank you. Okay. Talk is over. Okay, there you go. No, it's because this is, I think, one of the big hot topics right now is we have to come out and actually explain why you find phosphine on the atmosphere of Venus. That doesn't mean there's little green Venusians floating around in the atmosphere. If you find dimethyl sulfide, maybe, possibly, which I highly doubt in the JWST spectra, it doesn't necessarily mean there's life on that exoplanet, or even that exoplanet atmosphere could actually sustain life. Okay, making a jump from a molecule to life is incredibly difficult to do, and there's really a whole lot of steps in between that you have to account for. So this is an outline. Stop me anywhere in between. Okay, if you know some of the characters that are involved in this work, stop me, and I want to hear about it. Okay, because I only have like sometimes a second or third hand knowledge of what they were actually doing back at these times. And if someone was actually there or you actually heard some of these conversations happen, I want to hear about it. So we'll talk about the beginning. It's actually formaldehyde right down the road at 140 foot. We'll talk for the 100 more complex molecules, maybe some stellar mapping stuff. That gets a little weird because we got to use interferometers, and then what are the limits of molecular complexity going forward. So, where are we at right now? Here's happy birthday to a couple molecules in space. Ammonia is going to be 57 years old. We detected ammonia 57 years ago. Formaldehyde was 56 years ago. The big molecule that changed everything was carbon monoxide. We'll talk about that a little bit, and also exogen. What is exogen? Ever heard of this one? There was a transition in space that was found at around 88 gigahertz or so. Didn't know what the heck it was. Okay, they found it in space before they were found on Earth. There's other lines that have been found in space, specifically in the atmosphere of the sun, that were never found on Earth before. That's why it's given the name helium, because it was found on the sun first. It came from the term Greek word helios. So they didn't know what this molecule. They didn't know what the molecule was. It's about 88 gigahertz or so. They detected this in space, and they wrote a paper. And the paper said the detection of this 88 gigahertz line, we call it exogen. It probably had some carbon in it, maybe had some oxygen in it, but they didn't actually know what it was. It was only until years later that the spectroscopists in the lab classified it as HCO plus. But HCO plus in space was first labeled as exogen. Methanol was also detected, and then 51 years ago, I came into the world, as well as methylamine and dimethyl. So when you're talking about celebrating a birthday, these are the legendary molecules for me. Okay. After that, acetone was detected. Where do we find acetone? Nail polish remover. Acetic acid was detected. What's acetic acid found in? Vinegar. Glycolaldehyde. Ethylene glycol was detected 25 years ago. Antifreeze, not for your car, antifreeze for your spacecraft, right? Because the aliens are out there with the phosphine and dimethyl sulfide, right? They need to cool off their engines. And then another molecule that was detected about 20 years or so ago was cetamide and also C6H-, the first molecular anion in space. Anions were first theorized in the 80s to be detectable. No one found it yet. We detected it here first ever. Anions in space detected on the GBT about 20 years ago. This is right around when Sean Bean was Sean Bean was running around as in Middle Earth. That's when those movies came out about that time. So C60, C70, the first buckyballs in space about 15 years ago. C60 plus about 12 years ago. And then another big jump in chemical understanding was the detection of a benzene type molecule, benzonitrile. Again, first year on the GBT about 7 years ago. This has changed how we understand the formation of polycyclic aromatic hydrocarbons in space. We'll get to that at the end of my talk. And then finally, urea. Where is urea found? P. There you go. Okay. It's either 6 or 11 years ago. I'll talk about that story because I'm very intimately involved in that. Yes, my thesis back at the University of Illinois, all right, was on acetic acid and urea in space. Yes, my thesis was on piss and vinegar in space. I am literally here all week, but you only asked me to come the final day. And now Sean Bean, he came back as in Game of Thrones. That's about 15 years ago now, 10 years ago now, Game of Thrones came out. Yeah, that's where we're at. So, and then a couple years ago, 4 years ago, so 40 molecules turned 4 this year. That's crazy. In about 2001, we were detecting a new molecule in space for about once a week. And just give you some kind of context, to get that number up to 40, from 1937 to 1975, that's how long it took before we got 40 molecules detected. So this was a snapshot in time about how many molecules have been detected in space from 1937 to 2021, paced at about 6 molecules per year. This is what it looks like today. So in the last 5 years, we're detecting now about 21 molecules per year. Wow. It's incredible. This is what the GBT and some other telescopes around the world are doing. Better receivers, better technology, also better detection techniques. So this is kind of where we're at. This kind of complexity was unheard of 50, 60 years ago, but this is now routinely done in space. So my goal for today is to have a little fun, think we're hopefully doing that right, keep you awake. And pay respect to my advisor, Lou Snyder, who's at the University of Illinois, passed away in 2021. And so we had his retirement party here back in 2006. I have a picture in my office with my wife and my mother walking around the dish because we took a tour at the time. It was great fun, and I had a lot of respect for Lou, his family, everything he did for me, my family. So this is my homage to my advisor. And even though astrochemistry has been around for more than 50 years, we still don't have a good understanding of interstellar chemical processes. We just don't. Okay, you could go back to this guy named Einstein, pretty big back in the 20s of the last century. And he made a whole bunch of predictions, gravitational waves, a bunch of things that you can predict using his general theory of relativity from physics. You can then take all of those theories and take a binary neutron star pair. And you can test all of those fundamental theories of physics on that binary neutron star pair, all the way to emission to gravitational waves. It matches perfectly. I can't tell you that if you go to a laboratory and make a molecule in a bottle, and a series of subsequent molecules are formed after you combine these two molecules in the bottle, in the laboratory, put that to an interstellar condition and find those same molecules. We don't have that kind of understanding of chemical processes and how molecules are formed to go from what happens in the lab in a bottle to what happens in interstellar space. We just don't. And it's been over 50 years, we still don't have that understanding. And then finally, using all this to figure out what happens in this whole life cycle of chemistry, from a diffuse cloud into a dense cloud, into a star-forming, planet-forming disk, into the things that, like comets, asteroids, meteorites that form in our solar system. Does this chemistry, get contained all the way in this process until these molecules hit their like planetary systems? Or is it constantly reset after every single iteration? Does chemistry get reset from a diffuse to a dense cloud, from dense cloud to a disk, from a disk to a comet? Does the chemistry reset, or is it constantly maintained throughout this whole process? We don't know. And we still don't have the evidence to determine one way or the other. But we are starting to really now try to understand how these large molecules, from both high resolution spectroscopy and chemical mapping, how these molecules are formed in space. So we're in the Wayback Machine to 1969, to this seminal paper that changed the way we view the universe. So there's four authors on this paper: Dave Lou Snyder and Dave Buell. Anyone know them? Dave Buell was a electronic engineer back here in the 60s at Green Bank. Ben Zuckerman, University of Maryland, College Park, and Pat Palmer at the University of Chicago. No stories about Pat or Ben? Oh, okay, all right. But we're gonna talk about how Zuckerman and Palmer got on this paper, because it was kind of an interesting story, and we'll kind of figure out how at the time how proposals were handled back in the day. But at the time of this paper that came out, there were only 4 molecules ever known in space. CH and CH plus were detected in the 30s and 40s by their optical spectroscopy. So they were not detected in the radio, they were detected by their optical transitions. And any kind of thought of a molecule forming in space, there was this paper that was written by a Nobel laureate around that time saying that, this is impossible. Purely the spectroscopic criticism of this, it seems very improbable that these lines can be detected as molecular bands. There's no way molecules could form in space. Space was too empty. Space was too cold. Space was too extreme to actually find 2 atoms finding each other and actually forming a molecule. It was nonsense to think that these lines were actually due to molecules. But finally, years later, we're talking from the 30s to the 60s, and Sandy Weinreb was actually the first one to find OH in Cas A, and this was the detection of the OH molecule. So that low grade background in there, that was the off position, and here's this nice big absorption feature that is in the dark black, and this was the absorption of OH against the background of Cas A. It was done at about 1667 megahertz. Okay, and you can see there's about 20 or so channels across that entire spectrum. But this was the first real radio detection of a molecule, granted it was OH, and for 30 years span, that was it. there was only 4 molecules ever known in the entire universe at that point. Now Lou arrived. That's really a picture of Lou on his motorcycle in Charleston in the 60s. He was going to come out as a postdoc. He was going to come out and do your 2-year stint, and he wanted to look for water in space. And his buddy Dave, as it was an electrical engineer, said this was something they wanted to work on, and they wanted to use 140 foot to do this. Presented a whole paper. They were doing the WS. You can actually present this. But before, so again, if anyone knows the story, I want to know. But this is the story that Lou gave me when I was preparing these talks. He was going to present his talk, and he gets up like I did. He goes up, and you stand up, you're Charlie Towns, and you say, before we start here, I just want to let everyone know that we have detected ammonia at the Hat Creek millimeter wave antenna. Thank you. Please, postdoc, proceed.
Oh my God.
So then Lou has to go up there and say, so we're going to look for molecules in space, and no molecule's ever been detected, and we're going to look for water. Now, that was pretty rough for a postdoc to go through at that time. And what's even better is you actually look at the first ammonia paper that was actually detected. This was the ammonia transition that they detected. Is there a pointer? Oh, you have a stick? I'm sure. All right. So each one of those are individual spectral channels. That little stick figure underneath there, that's the ammonia hyperfine transition that you see. Okay, so the channels are up. What's even more fun is this, if you look at the top there, is how many hours they had to integrate at the very, very top. These first 3 or 4 channels, 2.5 hours. The next channels, 6 hours, and then 6 hours, and another 2.5 hours. In order to get, they didn't have enough coverage across the entire band, they had to do it in chunks. In order to see that line. And then this was the off position, just to make sure they were actually detecting the line. And this is the 2 to 2 transition. So that was the best transition of a molecule at that time. That's the ammonia transition that was done ahead. Pretty impressive, actually. So now's the time. Let's get serious. So this is Rick Simram. Rick Simram was a lab spectroscopist. He got involved in the project very early on, too, along with Frank Lovis, because you need the lab spectroscopy in order to get the transitions to go after in space. So they were serious about searching for larger molecules. NRAO was absolutely well positioned to do this. They had the receivers, they had the technology, we had everything. So how are we going to actually do this? Okay, ammonia, water we found in space, great. So Bill Howard, who was the assistant to the director at the time, said, look, instead of just looking for one particular molecule at a time, which was fine, what are all the molecules you want to search for? Go to your lab, find all the molecules you want to search for, and then submit a proposal to Dave Heshin, who was the director at the time, for both time on the 140 foot and on the new NRAO 36 foot out in Tucson. Now, again, sensitivity, you saw those 2.5 hours, 6 hours to do this. You know, months of observing time were needed on the 140 foot to search for molecules they want to. Nearly a full year, like straight up, give me the telescope for a year, and I'm going to search for all these molecules at the 36 foot. NRAO management, we being who we are, we're necessarily enthusiastic about that particular request. So again, if anyone was there, I want to know, here's how the story goes. Stoddard and Buell did what they did, good postdoc, good collaborator, wrote a paper, wrote a proposal. Dave Heshin says, dear Dr. Heshin, so on and so forth, we'd like to search for these molecules in space. And to paraphrasing the proposal review, now how many people have actually got a proposal review back and said, thank you, this is very good, however, you need to consider this, you need to consider that, so on and so forth. Dave Heshin's reply was basically, you are an irresponsible and ignorant PI to propose such a ridiculous thing. There is no way I'm going to give you a year of telescope time or months of telescope time to do this. What the hell are you actually trying to do? So imagine getting this as your response to your proposal as a new postdoc working at NRAO.
Just kidding.
Yeah, no, he wasn't. So there were 2 sides of this. Dave Buell, very diplomatic response back to the director was like, hey, we're trying to get people interested in molecules in space. Well. That failed to interest me. And then, but I'm not allowed to repeat what he said, maybe at the time. So, no telescope at the time was awarded for these characters.
None?
None, absolutely none. But I'll make you a deal. There's other real science going on, okay? So if you want to piggyback on some of these other observations that are doing some real science, then I'm happy, and if they allow you to, then I'm happy to give you the time. So that's for now. So Hat Creek is, Charlie Towns is at Hat Creek. Charlie Towns, Nobel Prize, he's at Hat Creek. We gotta get on the ball. We got a bad one here. So they made a deal. You can do these molecular searches under, with other observing programs. So this is how Ben Zuckerman and Pat Palmer came in. They're doing an 08 survey. So they're looking at the 1667 megahertz line. They're doing an 08 survey. So Lou and Dave's contact them and say, hey, can we piggyback on your observations? And if you're looking at this source, let's look for some formaldehyde. So that's the only way that this project got off the ground at 140 foot. Not from an accepted proposal, but hey, can we piggyback on some observations? And that's also how Zuckerman and Palmer got on that paper. They had no idea what they were doing. They just handed the telescope over and said, yeah, sure, go ahead. We're done. But that's how they got on the paper. And the rest is history. Spring of 1969 happened. They found the HCO, the formaldehyde line, and an absorption. And this is the formaldehyde absorption line. Wow. Getting a little bit better. A lot more channels, and we see a lot of different velocity structure. Here's the primary absorption line toward the galactic center. This is all the intervening gas and dust, intervening gas between us and the spiral arm cloud, us and the galactic center. Now, this was done in several hours at 140 foot. I took this data in about 2 minutes on the GBT. Exact same spectral line. Okay, and you just see the entire structure of the galaxy buried in there. All those little absorption dips are spiral arm clouds between us and the galactic center. Do a lot of now physics, a lot of chemistry of the diffuse interstellar medium when you're looking at transitions like this. So, fly was detected easily. This was in science, big news. They found it everywhere. Formaldehyde was everywhere. Everywhere they looked with the OH line, they found formaldehyde line. And then a couple years later, they discovered this should be 13 carbon CO. My typo there. They discovered 13 carbon. So the rest is history. That's how formaldehyde detection got started. And if you go down to 140 foot, I'm sure you've seen it. You see the plaque there, the first detection of formaldehyde. Questions so far on this? Are we having fun yet?
Yeah.
Okay.
Real quick, I am curious, do they just randomly looking at that frequency, or do they have certain where they're pointing the scope and saying, look, this is our best guess to see in this direction?
Okay. So when they were doing the OH, they knew the frequency of the OH. That was 1667 megahertz. And the lab spectroscopy that was done by the lab folks knew the transition frequency of the 1 to 0 formaldehyde line at 4860 megahertz. So what they were doing was when they were done with their OH observation toward one of these sources, just pick one, like W43, Lou and Dave were there, and they're like, okay, we're done. We found our OH line. You want to search for formaldehyde. So they switched frequencies, pointed at the same source, and took some observations. That's how they detected.
So literally piggybacking.
Oh no, it was absolutely piggybacking. And Palmer and Zuckerman had to agree to do this. There was not Dave Heaton said that we had to do it. They had to convince those folks to actually get them on the telescope.
About 1995 or so, at SARA conference, there was one of the scientists spoke about molecules in space.
Okay.
Said something about the Fisher scientific principle. He said you get the Fisher scientific catalog, which sells all kinds of chemicals, and if a chemical is cheap there, it says nature produces a lot of it, you're more likely to find it in space.
Oh, that's interesting. I can push back a little bit on that and say the space is ridiculously toxic too. And a lot of these molecules that you really don't want to find on Earth, they're ridiculously toxic. Some have to be synthesized on Earth here naturally, and not just formed. And some of the more exotic ones, like the anions and the HCO plus, they don't occur naturally here on Earth. So even some of these more simpler ones too. But you're right, that if you go through the Aldrich catalog, just kind of go and pick the simpler ones that are in high abundance and cheap.
He said if it's cheap, nature makes a lot of it. Let's see if we can find that.
Exactly. Interesting. All right. So moving on now, and we go to CO. CO was detected in 1970, so actually this was at 150 gigahertz. This was done by the Bell Labs telescope, and then more observations were done on using the NRAO. Get this one, 40-channel line receiver. So each individual point there was the CO line. But what's more fun is this. I like looking at the paper to the left. Anything interesting about this paper on the left? Just look at the authors. Look at the authors. Yes.
Yeah.
Very familiar. You should know a few of them.
Those and Penzias.
And if you are Wilson and Penzias, you get away with a one-sentence abstract.
Oh my God.
Right? I'm Arnold Penzias. I found CO. Drop it. Basically, I just finished writing a paper, okay, we find blah, 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 this molecule and this source of this rings in. Yeah, not Wilson, just, we found CO, and we're done.
Top that.
Yeah, exactly. Top that. And then, Thaddeus and Dave, they did this beautiful map, very, high resolution, large scale map of CO in the galaxy. And from that, they found this empirical relationship between the intensity of the CO line and the abundance of molecular hydrogen. Now I say empirical because it's exactly what this is. There's absolutely no theoretical basis, like we talk about theory in physics. I have a theoretical understanding of what's going on in physics. I can make a prediction. I find that in my observations. This is nothing more than an empirical observation. There's no theory here. There's no theory that says if I find the intensity of the CO line and I do a bunch of math and I understand the fundamental chemistry that's going on in space, I can get the abundance of molecular hydrogen. It's only an empirical relation. So just a lot of stuff we're talking about now is just, we find this, so it kind of looks like that. That's circumstantial evidence what we have. But this is used everywhere, all the time, all at once. Right? That was the name of that movie. I think people live on this. You go out and find the CO1 to CO transition, give you molecular hydrogen densities. Go find another one, molecular hydrogen density. Problem is, what happens when CO is optically thick and the intensity of the line is weaker than it was predicted? Oop, you abundant, you're then predicting the lower abundance of molecular hydrogen. Now you don't know how much gas is in your galaxy. Then you have to find this so-called CO dark cloud, all this kind of, because we don't understand fundamentally what's going on. All we're doing is empirical measurements. All right, let's go to a more complex spot. Okay, fine, we found formaldehyde, CO. Let's just jump to glycine. Why not? Look at this thing. That's a molecule of glycine. And it really was. I mean, the spectrum in the lab, it's easy. You buy it in a bottle, you throw it in there. You can buy a supplement, go to your general nutrition center, you can buy a supplement of glycine. And they just started searching for it in the late 1970s. And, Rick Sinram, who was a lab spectroscopist, and Frank Lovis, who also worked at the National Institute of Standards and Technology, they characterized this in the lab. They did huge searches for glycine starting in the 1970s, very shortly after these first observations were done. And you know what they found? Absolutely nothing. Observation after observation, telescope after telescope could not find any lick of glycine anywhere, no matter where they looked. But there was a lot of serendipitous discoveries. Again, we didn't really know what we were doing. Neither did these guys. You point at a certain frequency range and ooh, something pops up. What is this? This is the transition of what's called a molecule called methylformate. Methylformate is everywhere. Okay? So you found things like methylformate, formic acid. You know where you find formic acid?
Ant bites.
Ant bites. That's what makes it itch. Dimethyl ether and large cyanides are all found in these clouds. So these are two transitions of methylformate, very strong, very easily detected and arrived. And you can see our spectrometers are getting better, bandwidths are getting larger, but no acetic acid and definitely no glycine. Okay, and this is also how you tell like new students how to find molecules in space. We'll point the transition out to you with an arrow. Yeah, go ahead.
Ants in the molecular clouds.
We have ants. No, the ants are not in the molecular cloud. The ants are in the spaceship. Piggybacking, because they're having a picnic. Right, okay. With the ethylene glycol antifreeze cool off the spaceship engines. And I'm telling you, here's the molecule to go after. If you find hydrazine in space,
Nobel Prize.
you are writing that paper and you found the contrails of alien spacecraft. Absolutely 100%, I am waiting to write that down. So, we're happy because we're finding molecules, but we're sad because we can't find glycine. And this went on for decades, bigger telescopes, better spectrometers, all we see are the same thing. Now we're seeing seas of lines. This is from the 30-meter telescope, but no transitions of glycine at all, anywhere. So you see, okay, maybe you have a promising transition that's kind of floating here, there's a bump, but that's actually formaldehyde. Oh, here's an unidentified line, but it's nowhere near a glycine line. So we just couldn't find glycine anywhere. So results are always the same. Blank spectra or hugely confused spectra. And this can lead to erroneous detections. I'm going to give you a story now. We're going to change a little bit. We're going to jump forward about 10 years or so in the early 2000s, and we'll see how erroneous detections can easily be done here. So talk about, can we really trust the phosphine detection on Venus? Can we really trust the JWST spectra of dimethyl sulfide? This is not an exact science. I was sitting here in 2006 and I was giving this big tribute to Lou. He was retired, we're all talking down here, and one of the scientists comes up and gives a whole presentation, and he starts, I love this story, he starts the presentation, well, if Tony could do it, anyone could detect a molecule in space. Okay, fine. Fast forward 25 years, how many molecules has Remijan et al. Found? Probably around 30. This other guy? 0. All right, but anyone can do it. So let's talk about a bad detection. This is a bad detection. This is a transition of this is a molecule dihydroxyacetone. Pretty big molecule, but it's got carbon action. Okay, it seems reasonable. Here's what the spectrum looked like that they collected. Okay. Now you guys are all radio engineers, you right? Yes? Okay.
Yeah.
You know something about single sideband, dual sideband receivers?
Yeah,
What's the problem with a dual sideband receiver where you don't separate the two sidebands?
image.
You get an image plane, right? You get the two spectra, you get the two images folded on top of each other. So the Caltech Submillimeter Observatory had this problem in the millimeter. When you observed the spectrum, you didn't know if it was coming from the sideband you're interested in or the imaging sideband. They were folded on top of each other. Okay? Dihydroxyacetone is a big molecule. The more atoms in the molecule, the more transitions, the more degrees of freedom. You got CO, you got 2 atoms. You have basically every transition's at 115 gigahertz. CO is very simple. You get a molecule like this that's rolling, tumbling, and all this different degrees of freedom. You have a lot of different transitions. So they had one spectrum at the CSO. You didn't know if it was the image sideband or the regular sideband. And they made this prediction. With these 4 lines, 1, 2, 3, 4, I have detected dihydroxyacetone, drop them off. Not so fast. Because this is such a large molecule, it has a lot more transitions that you could go search for. A lot, thousands of transitions that you could search for. So we did what every good scientist would do. We looked for other transitions with other telescopes in other frequency ranges. And we find absolutely no evidence anywhere of dihydroxyacetone transitions at those other frequencies. This is what you end up doing sometimes. You end up policing detections because people are making outrageous claims with very limited evidence. You're making outrageous claims for JWST with very limited evidence. Making very outrageous claims of life on Venus with very limited evidence. So even though these people were good friends of mine, sorry, you did it wrong. No evidence of dihydroxyacetone. Now let's fast forward to a fantastic, marvelous, completely accurate detection, right? And we know why, right?
Yeah.
Okay. So I published this back in, what was it, 2014 or something like that. And I was skeptical because I did not say detection or claim of, I I did a multi-telescope campaign for interstellar urea, and I finally kind of found some stuff. That's what I said. But it was all self-consistent. Whether I looked at single dish telescope, the BIM array, CARM array, all my transitions were reasonable. I was finding it everywhere. But it was really hard to characterize. Until ALMA came along, and this guy came out, again, good friend of mine, Arnaud Deloche, comes out and publishes a detection of interstellar urea, found not only the ground state transitions, but also higher vibrational state transitions. I say, Arnaud, congratulations. Just curious, you say detection of interstellar urea, like the first detection of interstellar urea. I did that in 2014, you quote my paper. Yeah, but you didn't actually claim it. You just said you did a multi-telescope campaign and searched for it. Dude. So anyway, so it depends on how you look at it. Interstellar urea was detected either 11 years ago or 9 years ago, or 5 years. Anyway, up to you, you can decide. So the reason why, so this is what Lou said. It's like, okay, all these big molecules. All the theory says, with what limited theory there is, that these molecules had to be formed in hot regions. And if we use big single dish telescopes, you know, size of your beam, right? We all those telescope, big beam sizes, you're collecting all this information. You really can't differentiate between what's in a really hot region, a very cold region. You have all this confusion going on. So here's what we're going to do. We're going to build millimeter and submillimeter arrays. That's going to really focus down on the very hot regions, because that's where we think these molecules are formed. So he wrote this kind of position paper on why we need radio interferometers to detect large molecules in space. This position paper is really a fundamental paper that went into the development of arrays like CARMA and ALMA for detecting molecules in space. And it seemed like he was actually correct. Never underestimate Luke. He always seemed to be right. But when I started working with him, which I will go through this really kind of quickly here, kind of running out of time, but we started looking for molecules with the BIM array. This is a beautiful array out in Northern California. Now it's the Allen Telescope Array, and BIM became CARMA, and then CARMA got defunded. And so all the BIM telescopes, all these telescopes which I trained on, are now sold for scrap. Probably some part of some battleship or something somewhere. But this is a beautiful array of 10 telescopes out in Northern California. And this was the first detection of acetic acid in space by Dave Merriger. And not the greatest transit, you know, there were some lines you can see of this molecule, but I will make a claim that this is acetic acid is the only molecule that has ever only been detected with an array. It has never been detected with a single dish telescope. And it may be because of this idea that it's really in these hot compact regions. In addition to that, before ALMA came online, you have these maps being made of different molecules. And in the same source, so this is all Orion, but if I look at a vinyl cyanide molecule, it would appear up here. If I looked at dimethyl ether, it was in a completely different spot. Something interesting is going on in the chemistry here. Why are cyanides in one area? Why are oxygen-bearing species in another area? We're starting to understand now a little bit more about chemistry, maybe, by making these molecular maps. So this is Lou. Okay, Lou, you're right. ALMA's going to clean up when we do this. So you let's turn on ALMA and see what we get for these type of observations. That's what you get. Now, soak this in for a second, because this was ALMA science verification data. This is not even full ALMA, not 64 antennas. This was about 16 antennas. This was Orion in all of band 6, so 214 to 245 gigahertz. This is the most interferometric data taken on Orion ever in the history of radio astronomy at the time. So in the entire history of radio astronomy and radio interferometers, this 30-minute observation was the most data ever collected on Orion. With ALMA and not even cycle 0, this was science verification. It's an incredible amount of data. And you've heard the expression turtle all the way down? Right? What does that mean? Right? The universe is built on all turtles all the way down. There is no baseline here. Every single bump and wiggle is a molecular transition of something. It's estimated between 40 and 60% of all the emission coming from the Orion cloud is not from just regular radio continuum, but of molecules. So there is no baseline down here. It's all molecules. And for a while, it looked like it was doing pretty well. Okay, we found some new transitions across new molecules. Again, we have mapping information showing where these new molecules are coming from. This is a molecule called N-propyl cyanide. I was out of work where we see now methoxymethanol, not just regular methanol, but methoxymethanol. But what do you keep seeing? More and more lines all over the place. It is very, very, very hard to individually characterize any one of these lines because they're just in an absolute ocean, a New York skyline of lines everywhere. It's impossible to really pull out the lines of interest. So we need another way if we're going to analyze some spectra to not just look at individual transitions, because an individual transition can be very misleading. Here's methoxymethanol at this temperature. That's the energy of the transition. Here's methoxymethanol at another temperature. Here's methoxymethanol at another temperature. Here's something at 465 Kelvin. This is methanol. This is one at 300 Kelvin. So if you're looking at not only the molecule, but the energy of the transition, they all look different. Some of them look the same, but a lot of them look different. So we developed a technique in order to combine all these transitions together to make not just a transition map, a map of a particular transition of a molecule, but an entire chemical. And when you start doing that, you see maps that look like this. You have glycoaldehyde where you have absorption in one region, and then peaks of emission in another region. Acetic acid, really compact and small and hot all the time. Methylformate is everywhere and extended and cold. But this is kind of what we now are doing with astrochemistry with ALMA. We're trying to combine all the transitions to make a singular chemical map, not just looking at individual transitions. So far, so good? Are we tired yet? Yeah, we are. I'm tired. All right. But this just kind of summarizes where we're at for molecular emission. Here's the problem with all of them. It did not give the water set of new molecules. You know, Blue thought this thing's going to turn on, it's going to be molecule after molecule. I'm just going to go, right? Because you're going to have all these high energy transitions, high frequencies, high temperatures. This is where everything's at. Actually, turned out wasn't the case. If you look at the proposal of the Green Bank telescope, centimeter, if you're going to find big molecules, real big ones, the centimeter region, okay, is going to be key because that's where a lot of the stronger transitions are for these larger molecules, and the line confusion, the total number of lines down at these lower frequencies is much smaller. So this is the brilliance of the GPT. And this is where we're at right now. Okay, so we're going, I got one more story to share, but I want to walk through this a little bit quickly. But this is what we're seeing now for in the torus molecular cloud on transitions of what we found a couple of years ago called benzonitrile, the first real true polycyclic aromatic hydrocarbon. We're seeing individual transitions now of these molecules. And you can see the data are nice and clean. You don't see a lot of contamination from other lines, and the lines are popping up above the noise. We can do better than this. Let's take an even bigger molecule. 1,2-cyanamnaphthalene. All right, naphthalene. Where do you find naphthalene?
Dry cleaning?
Mothballs.
Mothballs, yes. See what I'm talking about? Toxic? Vinegar. Ethylene
Aliens
glycol,
wear a lot of wool sweaters.
naphthalene. Okay, what?
The aliens have a lot of wool
So
sweaters.
there's a lot of problems out there, right? And they're trying to take care of it. But what do we do here? When we talk about this, spectral match filtering, what are we doing here? Well, molecules like this are very big. They have all these transitions all over them. Okay, and they're very well separated, very well characterized, but some of them are very weak. So what we could do is we could take the thousands of transitions that are in the spectrum, line them all up because we know the source very, very well, and stack them on top of each other and average. Okay, signal averaging, right? Because we know where all these transitions are, we can line them all up in velocity space, add them all up together, and make one characteristic transition. And that's exactly what we do. When we do all that, we combine all data together, we get a sum spectrum, and because we know what the velocity structure is, we run something called a match filter through it. So we have a line profile that we run through the entire spectrum, And if anything lines up with that profile, that actually gives us a peak response function over here. So these transitions, these molecules are only detected at a like 17 sigma significance. Individual lines may be very, very hard to detect, but the match filter and the spectral stack are very easy to detect. So we're using the sensitivity of the GPT, spectral resolution of the GPT, and these new advanced techniques of data processing and averaging in order to detect these new molecules in space. That's why we're seeing 20 molecules a year now, because we're using these new techniques. Last story, HC11F. Love it. There and that again. That's the story that I talked about for HC11F. 140-foot telescope in 1997, it came out. Bell and his colleagues up at the CFA, Carl Gottlieb was in there, Pat Thaddeus was in there. They found the largest, the HC11F is exactly what it is. Hydrogen, 11 carbon atoms and a nitrogen. That's what a big long chain. They detected 2 transitions with 140 foot. Problem is, these transitions were never seen again. Absolutely not. This was like one of the last observations they ever took on the 140 foot, and then they shut it down. It was crazy. But these 2 transitions were never seen again, and we looked. We looked at the GPT. We pointed the GPT at exactly those frequencies, stared at it forever, and couldn't find those transitions at those frequencies. In addition, we did a stack very, early on, back in 2016, a very early stack, couldn't detect this molecule. But it wasn't just us, our colleagues did the same thing. They tried looking to get exactly how strong would the bell lines be with these observations in their data. They couldn't find it. We have no idea what those lines were. They do make some offhanded comment that, oh, because we did this, because we did that, and there's frequency switching and all this kind of stuff, we can't completely rule out that these features are introduced by the correlator. Maybe. Turns out they weren't. None of this is real at all. So old technology, none of that was real back in the late 90s, because we never saw those lines again.
Or
So
they found a dust buster.
Huh?
Or they found a dust buster, vacuumed it up.
Who's they? That's the thing, you gotta ask who's they. So it was there, and then we wrote a paper and we got rid of it. And it's still gone. And then we did this and it came back. So again, it's an interesting story about how this molecule was there, then gone, then back again. But we don't see any individual transition of the site. So this is all the data that we collected, dozens of transitions. But when you combine the data and spectral average them and you put them all together and then you run this match filter through it, the line does finally appear in the data. But it takes dozens and dozens of transitions to do this. And now the most recent detection that came out as a press release this week at the AAS on SAN and chlorine, we're talking thousands and thousands and thousands of transitions that we do this now and finding the biggest molecules ever detected in space. So here's where we're at. Telescopes are big. This is a couple years ago, but once the GPT turned on, boom, we're accounting for about 20–30% of molecules out in space. So the Yabis 40 meter and the GPT are absolutely cleaning up in this field. So these numbers have grown huge since then. Now, I'll leave you with this, and we'll conclude here. Back to the idea of chemical theory and chemical understanding. We don't know how these molecules form. We don't know where these molecules form. And even if we think we know something about their structure, that doesn't tell us what molecules we're going to find next. So here's the formaldehyde, our aldehyde family, I call it. Formaldehyde is at the top. It's very simple. You have CO and 2 hydrogen atoms. If you replace one of those hydrogen atoms with a CH3 group, you get acetaldehyde. That molecule is detected in space. You replace one of those, the other hydrogen atom with another CH3 group, you get acetone. That molecule is being detected in space. You go the other way. You replace one of the hydrogens with an NH2 group, you get formaldehyde. We detected it. If you replace the other one with an NH2, you get urea. We found that. Kind of going in the middle, if you take your acetaldehyde and replace the hydrogen with a nitrogen with NH2, you get acetamide. We found that. But that's it. That's the limit of our molecular complexity for this family of molecules. Every one of these things where you just add another CH3 group, none of these molecules have been seen. This one's been claimed, but we shot that one down too. But this is what I'm saying, is, we think we understand what's going on in chemistry. Okay, these molecules all look the same, they're all of the same family, this, why do we see one set of molecules instead of another? Same thing with the water family. So you start with water at the top, you get to dimethyl ether, fine. You go the other way, you get to hydroxylamine, but then when you go to two nitrogen and H2 groups, you don't see anything. So when I give this lecture to students, I say, this is your challenge. Tell me why we stop here. What is going on? What don't we understand about chemistry? What don't we understand about the physics going on in these sources to actually form these larger, more complex molecules? Because if you find that out, combined with the mapping campaigns, combined with everything else we know, that's really going to give us the Nobel Prize. Not finding a particular molecule, crap aldehyde in space, no one cares about it. Okay? They don't. If you tie it to, hey, it may be life, then they start caring about it a little bit more. But if you start getting, we understand interstellar chemistry, and I can tell you how all interstellar aldehydes form in space. That means you understand fundamental chemical theory. That means you understand fundamental chemistry. That gets you Nobel Prize. That's what wins. You understand Nobel, you understand physics, and you test it, that's what gives you Nobel Prize. Finding another big molecule in space, I tell the students, no one cares about. You understand how this works and why we don't see this from a theoretical point of view, that's what will give you Nobel Prize. So I'll leave it at that. All this other stuff, blah, blah, blah. I have no idea how to get there, okay? That's why I give it to the students, okay? It's the same thing. I have no idea how to get there. So I just thank you for your time and attention. Hope you were entertained for the last 45 minutes or so. And happy to come back and talk.
I have a quote, but I don't remember the author exactly, but it's something like, organic chemistry is a dark forest, and once you enter it, there is no way out.
Yeah, I feel that. And that's why all my colleagues are they're physical chemists, right? They understand physical chemistry, right? You put the rather from theory, you put the molecules in a computer program, it makes it structure, then it can generate a spectrum, and then you can actually do work on that. But the organic part of it actually synthesize in the lab. You're exactly right. We go knock on doors. And yeah. Hi, we need to synthesize this molecule. What? I mean, they don't know how to do it. Then it's literally just going in and trying things because they don't have the really good. And some of that can be pretty dangerous at times too, from what I hear. But yeah, but that's the thing is you want to go into the physical chemistry. The physical chemists love what we do because it really nails down, especially spectroscopy. They look at when I bring our GBT data or ALMA data to the lab spectroscopists. They're like, this came from space because it's as good as or better than what they do in the lab. That's really what they say. And we matched them up. We have multiple papers where you have the lab spectra right on top of the GBT. And channel for channel, the GBT data is just as good as the laboratory data. Down to the signal to noise. It's amazing. So they love it. The organic chemists, wait a minute, you want us to run chemistry at one atom per cubic centimeter at 3 degrees above absolute zero, and you want us to do chemistry? Well, yeah. I mean, the torus molecular clouds at 5 Kelvin. There's approximately 10 atoms for every cubic centimeter, and we see the largest number of PAHs ever detected. They're like, that can't happen. PAHs, polycyclic aromatic hydrocarbons, are only produced in flames. They're the stuff that gives you the crust on hot dogs and hamburgers and steaks when you barbecue. That's exactly what they are. That's how you produce them. You don't produce them at 5 degrees above absolute zero. Get out of my office. And then they call, and then they say, there's a guy downstairs. Security. You may want to watch him, escort him out of the building. Crazy stuff at absolute zero. But that's exactly, there are no, papers in the chemical journals on forming polycyclic aromatic hydrocarbons at 5 degrees. There just isn't. Or 5 Kelvin, not 5 degrees, sorry, 5 Kelvin.
And you mentioned the image problem, kind of confusing spectral lines.
Yeah.
Way back in the early 70s, I used a spectrum analyzer from HP that was ancient at the time in my job. And in order to sort out things, because there were so many spurious responses, you had a button you pushed and it moved the local oscillator.
Yeah.
specific amount. Then the line you were looking at, you'd see how far it moved on the screen, and that would tell you if it was plus or minus. And if it moved
Absolutely.
1, 2, or 3 or 4, it'd tell you which harmonica the local oscillator was beating with. And you had to sort it that way because there were so many spurious responses in a mixer.
And and for my, I don't know, for my credit, for not my credit, I don't know how you want to, I gotta say it. But you know, Lou taught me, just don't believe it. Okay, if it's too good to be true, probably ain't right? But you know, and so when a new molecule comes in from our group, they send it to me first. You're like, here it is, what do you think? I'm like, absolutely no way, no way. And we'll go, and we will go through every, I try to shoot it down, they come back, try to shoot it down, they come back. But this is exactly right. You see these two lines, the first thing you should do is move the local oscillator on 140 foot and see if the line moves. Same with the CSO spectrum from, you know, where the dihydroxyacetone, they should have jiggled around, they should have moved the LO around, because the image band will move.
Yeah,
right?
They move
Right,
relative
and they
to
move
each other.
relative to each other, so they can determine whether or not the lines that you were seeing in your non-image, in your, what's it called? Not the image one, the one that you're tuned to.
Yeah.
It doesn't, do they stay still or are they moving around? They didn't do that either. So there was just so many of these, you know, and when that paper came out, they said to me, oh yeah, we found it. I'm like, no, you didn't. Here's this problem, here's the problem. Oh, no, but yeah, we did. I'm like, you need to do more work on this. You really need to do more. I'm warning you, please do some more work on this. Don't publish, you're gonna publish, you published it. Oh, okay, well, here we come. Because, you know, the paper comes out and then my consortium gets on and we're like, okay, well, we have all this data, we can show that it isn't. And there were a couple other molecules too, like, another group, they published, and it's just like, it's intuition, this hydroxylamine is weird. Okay. Methanol was, 50 years ago, methanol was used to be detected. Hydroxylamine is just an NH2OH, okay, very simple molecule. And again, talk to the theorists, they come out, they have a model of hydroxylamine, they publish this paper. Oh, hydroxylamine should be about this abundance in interstellar space. Hi, it's me again. No, it's not. No, but we run our models, we run our chemicals, like, have some chemical intuition. If that abundance was true, that you're claiming in this paper, we would have found it in 1973 with 140 foot. It's trivial. We have absolutely detected it back then. They're like, oh no, but this, that. I'm like, no, really. We would have detected it 40 years ago. And just kind of proceed with the paper. So we write a paper and say why it's not there. It's detected, which actually was good. That's how science is supposed to work, actually. Because our papers then spurred a whole bunch of other experiments, not just theory, but actual experiments, people doing stuff in the lab. They're like, oh yeah, really, that reaction network doesn't go. It doesn't work at all. It's a huge barrier. And so kind of followed up on why we're not seeing it. And that actually spurred a whole series of papers until they actually found it in some weird source.
Well,
But yeah, you should dither it around.
we did find life on Mars, no. Published paper long time ago.
Did we?
No.
Oh, okay.
Remember that paper that got published?
Oh, yeah. The microbacteria that, yeah.
Really 2401.
Yeah, the mycobacteria that was also cold fusion back in the 80s.
You might have answered this at the end of your talk there, but just out of curiosity, as a new, like, you detected methanol.
Yeah.
Does methanol, does it change in interstellar space, meaning like you might not see it anymore? Does it get destroyed? Does it
I have
volume change?
Yeah, I have a hidden slide here about it. Methanol is, if methanol is reaction in another formation around to another molecule, we'll never notice the difference because it's so abundant. Like CO is used for a lot of different reactions. CO is so abundant, we're never gonna see it dead. But for some other trace species, we're actually starting to see this, where you see one molecule kind of peaking up, the other molecule kind of going away. And so we're now starting to see this for some of the other trace molecules, but they have to be trace species. Methanol, HCO, HCO plus, ammonia, they're so abundant everywhere that we really can't tell if they're coming or going. But some of these other trace molecules can.
As far as detections and things, do you see a lot of where we have just a ton of data that still hasn't been analyzed, or no, all this is live on telescope?
No,
With a mixture.
no, like the cyanopornine and stuff, what, this stuff is just sitting on this. And sometimes what it'll take is, you know, again, so I have a whole consortium of like lab chemists and, you know, and physical chemists and stuff, and I say, hey, how about this molecule? And they laugh at me, they're like, how do you, this? And they draw it on the board, they're like, yeah, I guess I could go. I mean, the molecule that I wrote on the board was this. Kind of right on the board. Oh, it's your stuff. This molecule. Sigma H, C3H2S. It's a 3-member carbon ring with a sulfur attached to it and 2 hydrogens off of it. And all the bonds work. I mean, there's 2 bonds here, 3 bonds here, it all work. So all you gotta do is characterize in the lab. You gotta synthesize it first somehow. You gotta synthesize it. And so someone made it through an electrical discharge, ran the spectrum on it, and they're like, okay, then all the GPT data are just sitting on disk, and then we just run it through our analysis routine like we do here, and lo and behold, there it is, it pops up. So it just takes some of the
Whatever you dream up.
yeah, it's like, oh, and I dream up all kinds of crazy stuff that don't pan out, but you know, that's fine, that's how we do it. But it's, I mean, but again, it's not necessarily chemical intuition. I just kind of look at it and go, well, some of these other molecules are there that look somewhat similar. Why wouldn't this one? Sulfur's pretty abundant in space. Might as well.
How well defined are the biosignatures relative to the non-biosignatures? Is that a highly debated
What do
topic?
you mean define?
Well,
like, how
I guess,
do we
I
know
guess
that's a biosig-
categorization from the standpoint.
No,
Is it well defined or
no,
is it still
it's not.
very?
No, it's not defined. I would make the argument there's only one true biosignature. That's a chlorofluorocarbon. That's it. Because any other molecule that you can think of could have some abiotic formation process. A CFC cannot. CFC has to form a manufacturing, and that's how you're gonna find aliens. They're polluting their atmosphere. But fine, carbon dioxide. No, that is abiotic processes. Dimethyl sulfide has abiotic processes. We found dimethyl sulfide in space. You cannot. We found the phosphine one really pisses me off. I'm sorry, because phosphine was detected on Jupiter by Voyager in the 70s. No one made a claim. It was detected in the 80s in an evolved star called IRC 1016. That's interesting. Phosphine's there. Okay. No one said there were aliens on Jupiter at the time. No one said there were aliens on this evolved star at the time. But you know, found it in Venus and found it. We could debate that for another hour. I would say not. All of a sudden, life on Venus, it's been known since the 70s. We found it in space. So yeah, I would say that there is no consensus, and I will go to a AAS meeting and they're talking about, you know, dimethyl sulfide, like that's an extraordinary claim for life. You really need some extraordinary evidence, and a single molecule is not that. I'll say that. It's just not. So it's just
Other hidden reasons.
Yeah.
Go one more to.
How do you decide where to look?
because that's what molecules are.
Well, I mean, galactic center, Andromeda, where do you decide to point?
Because that's what molecules are.
Anything else?
This was Lou's response to me. So I'm like, what? He's like, well, that's where the molecules are. Well, how do they know that they're there? Because we looked. Okay. I mean, I'm like, are these things unicorns? A little bit. They're unicorns. I mean, TMC1 is one of many dark clouds in the galaxy. There's just a lot of stuff there, and it's really close. But is this chemistry present in these other dark clouds? Yeah. We've done large surveys.
So you want to try to be close.
Yeah, but I mean,
dense.
but we're trying to expand to other sources, just like they did. However, it takes telescope time. And how dare you request hours and years of telescope time? You have not impressed me. I still get that same response in my proposals that I write. I'm a damn director. Literally, I put a large proposal. It's like, yeah, we're not convinced. So bad.
We know time is precious, so thank you very much. Not only for your time, but we thank you for Green Bank just hosting us over these years.
I have